Okay, good afternoon, everyone. Welcome to today's TSVP talk. It is my great pleasure to introduce today's speaker, Professor Cintia Pacchiano. Cintia holds a PIMS postdoctoral fellowship at the University of Calgary. Her research area is mathematical analysis and nonlinear partial differential equations. Her focus is on regularity theory of elliptic and parabolic equations, calculus of variation, potential theory, and recently analysis on metric measure spaces. So today, she will talk about variational methods and metric measure spaces. So please.
Okay, hello everyone. First of all, thank you for the introduction. Thanks to the SVP for giving me the opportunity to be here. It's been amazing, and thank all of you for being here. So as already been said, as you can see today, I will talk about variational methods and the connection with doing analysis on metric measure spaces. So I know that this is a broad audience talk, so we're gonna go very basic and then start building up theory all the way to one of my projects. So let me. So that I always forget if it's the right arrow or the below, but it's not working. Okay, good. Okay, so we start with an introduction to differential equations. And well, I said we're gonna go super basic. So here we have a linear equation. And I'm gonna go on a limb and say that I think everyone here knows how to solve such an equation, right? It's a linear equation, just one unknown, and if I'm not mistaken, the answer is equal 3, right? X equal 3 solves this equation, and x equal 3 is kind of like easy, right? It's even tangible. Everyone knows who x equal 3 is. So this is very, very simple, but what happens when instead of looking for numbers, we look for something a little bit more abstract, a little bit more complicated, something that it's called a function. And if you're not familiar, it's fine. In mathematical terms, a function, we can think of a function as some sort of bridge. So we have set A, any set A, and then we have any set B. And what a function does is, well, we grab points in set A, and a point in set A, with the function, we assign it to one and only one point in set B. That is a function, right? And well, I like to give this example to my first year students. Think of your favorite movie, okay? And define set A as the set of actors, actresses in your favorite movie. Now define set B as the characters in your movie. So the function assigns each of the actors and actresses to the character that they are portraying, right? So in my case, for instance, my favorite movie is The Lord of the Rings. So the actors here, Ian McKellen goes to Gandalf, right? Elijah Wood goes to Frodo, and so on and so forth. Now, this is obviously a very simple example, right? It's a discrete function, very, very simple, but things obviously, as you can imagine, can get quite complicated. These being sort of very abstract, they can go wild. And remember now, we're interested in equations whose unknowns are these things. So a little bit more particularly, we are interested in partial differential equations. Now, a partial differential equation, which from now on, I'm most likely just gonna refer to it as a PDE, is an equation involving an unknown function of two or more variables and certain of its partial derivatives. This is just something taken from the kind of like the most famous book about PDEs by Lawrence Evans. And just to have a little bit of a more formal definition, a mathematical definition, well, we have an expression, and I'm just gonna, does this one work? No, I'm just gonna point it with the cursor. So we have an expression of this form, right? So f that depends on certain function u, x, and well, the derivatives of the function u equals 0. And we call this expression K-ordered partial differential equation, K because, well, there's a derivative up to order K here, right? But kind of like what we already knew is that the unknown here, it's a function. So there are different types of PDEs. We have linear PDEs, semi-linear, quasi-linear, non-linear. Obviously, with its corresponding difficulties. I'm not gonna give all the details regarding these difference in definitions. But before going to explicit examples, let me go back a little bit to the linear equation. Okay, so when kids learn to solve these, usually comes with some sort of a statement, a real life statement, something like Pedro has 15 pineapples and wants to buy whatever, right? Like some sort of wannabe real life statement. And what the kid has to do, well, they have to understand that statement, come up with an equation, right? And then solve the equation. So with PDEs, something really similar happens, right? There's usually some sort of motivation. We have the physicist or the biologist, I don't know, that thanks to observation or experimentation, they realize that there's some sort of phenomena going on. And then comes the modeling part, and we have now a PDE. Okay, so let's see just some examples. Kind of like the most famous examples of linear equations. For instance, we have the Laplace equation, which in mathematical terms is the sum of the second derivatives of a function is equal to 0. Now, what is the physical interpretation of such an equation? Well, usually the function u here can represent some sort of density of a quantity. If we're asking for the Laplace or this operator to be equal to 0, then we are in a state of equilibrium. Okay. We have other examples, the linear transform equation. Unfortunately, I'm not going to go through what are the physical interpretations of each of them, but we have other examples of linear equation, the linear transport equation, the heat or diffusion equation, the wave equation. And well, for these three last ones, notice that there is this like partial derivative appearing, so a partial derivative with respect to the time. We are now working with a function that not only depends on the space, also on the time. So we call this type of equation parabolic. And other examples are nonlinear equations. We have the nonlinear Poisson equation, the P-Laplace equation, which is one of the ones that I've worked with the most, the minimal surface equation, Monge-Ampere, and porous medium equation. So this is a nice looking list of examples. But what now, right? Now, the most naive, I guess, thing that a mathematician can expect or to think is, okay, is there a way, is there some sort of method to solve them all? And well, I say naive because as you can see, lots of different examples and also lots of motivations behind these PDEs. So, well, it might not even be possible, but what is the strategy now? Now, as a mathematician, whenever I come up with a PDE, the natural question that arises is it well posed, right? And what I mean by that is the following. So we say that a given problem for a partial differential equation is well posed if the problem has one solution, has a solution, right? And not only that, we ask for the solution to be unique. And furthermore, we want for the solution to depend continuously on the data. Now, this last point, it's important, for instance, when the motivation comes from physical problems, because, well, if the components of our problem change a little bit, we would like for the solution to change accordingly as well. So this is what it means to be well posed. But something that I have not told you guys is what does it mean to be a solution for a PDE? Now, if we go back to the naive kind of goal of solving them all, then what? Should we ask for a function to be infinitely differentiable, well, that's a lot. Obviously, that's a lot. But if we go back, let me just go back really quickly to the definition of PDE. If we're working with a k-order partial differential equation, obviously we are looking for a function that not only satisfies these, but I mean, it would be nice to at least ask that the kth, that is k times continuously differentiable, right? And that's actually the definition of being a classical solution. A function that obviously satisfies our equation and that is at least k times continuously differentiable. But, and let me go back to the slide that I was in, that still might be a lot to ask for a function to be h times continuously differentiable. So we know that there are PDEs who indeed have a classical solution, such as the Laplace equation. But if we focus for a moment on the following one, so the scalar conservation law, what these equation models is formation and propagation of shock waves. And what happens is that a shock wave in a solution, it's precisely a curve with discontinuity. So if we are looking for solutions for this type of equation, then we must allow for this solution to be, well, not continuous, right? So we cannot ask for classical solutions. So what do? Well, we weaken our notion of solution. So we can now start thinking about, okay, weak or generalized solutions, right? And since we are asking less, I mean, we are not gonna ask anymore for k times differentiable, right? We are gonna ask a little bit less. So what might happen is that proving existence of this type of generalized solution is easier. And once we have existence, then we can work with what we have. We can then try to prove and focus on studying smoothness or regularity. And it might even happen that this generalized solution is continuous enough, like k times differentiable, and it happens to be a classical solution that we were looking for. And this is very important. What I just said, it's very nice because I think it's what mathematicians do a lot, working, now how is the saying? Work smart, not hard, or something like that. Because, I mean, just the fact that we are kind of looking for something that it's easier. I mean, yeah, we are gonna most likely, hopefully, being able to find these new concepts and then work around it, and then maybe get what we were initially looking for, right? So let's focus on this type of generalized solutions and proving existence. And this is kind of like a nice way or a nice segment to start with variational methods. So again, we want to solve a certain PDE, which for simplicity, let's just write it as some nonlinear partial differential operator, A equals 0, right? And furthermore, let's assume that this operator actually is the derivative of some sort of energy function. So this means that we can rewrite equation 0, 1 as the derivative of I equals 0. And let me say something here. This is beautiful. Mathematically speaking, I think this is beautiful because what we just did is, okay, we start with a PDE, right? And then we are rewriting that. And instead of solving a PDE, what we are doing is, well, now we want to see where a derivative vanishes. And this problem of where does a derivative vanish means that we are looking for critical points, right? To say this in another way, we might be looking for minimums or maximums of a certain energy functional. And I think this is very nice. Yes, sorry? Sorry?
Derivative with respect to space or time?
So the thing is that it's an operator. So actually this thing is evaluated in a function u. But yeah, well, it also depends on what type of of variables I'm working with my function, but this is just an operator that is from somewhere to R.
So does this reformulation always exist?
No, not necessarily. Yeah, no, and actually, we're gonna because what we started with, like with this technique, is by assuming that precisely the nonlinear PDE operator, we can see it as the derivative of an energy functional. So that's kind of like the key point. So let's see some examples actually where that happens. So for instance, if we work with this energy functional, then the associated Euler-Lagrange equation is the Laplace equation. Okay. Now, if we work with this energy functional, then the associated Euler-Lagrange equation is the nonlinear Poisson equation. And lastly, if we work with this operator, then the associated Euler-Lagrange equation is the minimal surface equation. Now, I want you to notice some things. If we focus on the PDEs, well, this is the Laplace operator, so we already know that this is the sum of the second derivative, right? So I'm talking about taking derivatives twice. Here as well, right? We have the same operator, so I'm taking derivatives twice. And the last one as well. It's the divergence of a derivative, so I'm taking derivative twice. But if I now focus on the energy functional, well, I only need kind of like first order. I'm only taking derivative once, here as well, and here as well. So I'm kind of lowering the order of calculus that I need. So let me give you a little bit of history about variational methods. So as we already know, many phenomena in nature, I don't know, physics, biology, medicine, finances can be modeled by a partial differential equation. And what we just saw is that many of these models can have a variational formulation, meaning that the solutions to the PDE are going to be the critical points of a certain functional, right? Energy functional. Now, since in nature, it's relatively common to have what it's called an equilibrium potential, then that was enough reason for Gauss to say that, well, then the integral must attain its minimum or its maximum. But it was until the end of the 19th century when Weierstrass here realized that there's an actual difference between real life and the mathematical model. And Weierstrass actually gave an example of an integral that does not attain its minimum. But that's fine, because that's precisely the initial point where calculus of variation started developing. Now, let's focus again on the following example. So the P-Dirichlet integral, right? So we have this energy functional. We already know that the Euler-Lagrange equation associated to this functional is the P-Laplace equation. And to make things easier, let's make P equal to, okay? So if we focus only on the PDE, when P is equal to, we have the Laplace equation, right? We return to the Laplace equation. And we already know that, well, that means that we were looking for some sort of state of equilibrium, or to say it in mathematical terms, when the Laplacian vanishes, we are looking for harmonic functions. But looking for harmonic functions is not a trivial problem, because it even depends on the domain that we're in. It's not trivial. That's kind of like what I want you guys to know. So this need to look for harmonic functions pushed Riemann here to think of the problem in a different way. Riemann was, well, what if instead of focusing on the PDE, I actually focus on the integral, right? So I focus on the integral, I study the integral, and then get all the properties just solely focusing on the integral. So basically, Riemann gave us the Dirichlet principle, and with that, he basically gave birth to the direct methods of calculus of variation. And that is very important because people start to realize that, well, maybe we can still have all this amazing theory for partial differential equations without actually having to rely on the partial differential equation itself, right? And not only that, well, we already have seen that somehow we are lowering the order of calculus that we need. So what if I start to generalize things in spaces where we still have some sort of differential structure, but not like the one that we are used to in R or in the Euclidean case. And this is precisely where my work comes. So the main motivation for my work has been to extend some classical results of the calculus of variations to metric measure spaces. I have focused on methods which in the Euclidean spaces relate to existence and regularity of nonlinear parabolic and elliptic partial differential equation. So we have seen some typical nonlinear variation problems are the parabolic P-Laplace equation as well as just the elliptic P-Laplace equation. And well, what are the advantages of working in this general setting? Well, it gives us a unifying framework, right? It not only has applications within mathematics, it can also have application in other disciplines like computer science. Since we are working in something more general, it can lead to new results, new even in the Euclidean case. And well, the last point might be a personal advantage, the fact that we have access to all these rich nonlinear PDEs theory that makes it very interesting. So far, I've talked about an introduction to PDEs, an introduction to variational methods. But remember, the main goal is to be able to do variational methods or to stay in some sort of variational level and do analysis there, but on metric measure spaces. So now let's continue with the definition of metric measure spaces. And some of the most fundamental notions in mathematics, like limits, so approaching somewhere or like someone approaching another thing, that it's defined exclusively by using the notion of distance. So this is why we start with what is a metric space. And the French mathematician Maurice Fréchet was the one who introduced this notion. So we have a set X, any set X, and we define a metric or a distance as a function, right? A function that satisfies three things. That the distance from a point X to a point Y, it's 0 if and only if I'm talking about the same point. Now, the distance from a point to another, it's the same if I go kind of like the other way around, like if I start with this point and go to another. So we have symmetry. And the last one is called the triangle inequality. So basically, whenever we have 3 points, the distance from this point to this point, it's less or equal than the distance from this point to this point to this point, right? Plus this. Oops. Okay, good. So this is a metric. And to be fair, I wanted to give more examples, right? But I think this is a very intuitive notion. So I know that the distance from me to the whiteboard, well, we can measure it or know it by a straight line, right? But I can think also in the Earth. The surface of the Earth is a sphere, and I know that there's a distance between Mexico City and Helsinki, right? Like there's a way to knowing that distance going along the surface of the Earth. So those are two different notions of the set X and also the function distance that we are defining. And also for one set X, we can have many distances. It's not a unique concept. So it depends obviously on the type of problem that you're dealing with. But if you're more interested, actually, so Jana Bjorn, Professor Jana Bjorn, she was recently here and she gave a talk about more things like this. I watched her talk. It's on YouTube because I didn't want to repeat what she said. So you can check that if you're more interested about these type of notions. So a metric space, it's precisely just a set X with a metric or distance defined, right? But we're also interested in measure spaces, right? So the measure, again, is a function. This time it's going to be a function defined in the set of subsets of our space. So we say that mu is an outer measure if, again, these some three conditions, right? So the first one is that the measure of the empty set has to be 0, which makes sense. Like the empty set, well, it doesn't have anything, so it has to be 0. Now, we also have that if a set is contained in another, well, the measure of the one that is contained has to be less or equal than the measure of P, right? So we have monotonicity. And the last one is that the measure of a countable union has to be less or equal than the sum of the measures. So we have countable subadditivity. So those are the two concepts that I kind of want you guys to know. So we can actually move on to our setting. Now, again, our goal is to do variational methods and metric measure spaces, but it's not like we can just start doing it. We need to understand what is it that we need to ask our space in order to be able to do this type of job, right? And unfortunately, when we generalize things, we might lose that comfortability that we had when working on Euclidean spaces. And I'm gonna say a little bit more about that when it comes, but okay, so we start with X, a metric measure space, and this might be a little too mathematical, but the first thing that we need to assume is for X to be complete, separable, connected, and endowed with a Borel doubling measure mean. So what does it mean for the measure to be doubling? And I don't know why they never work my links. Okay, so for the measure to be doubling means that the measure of the ball with double the radius is bounded by a constant times the measure of the ball. And this must hold for any point and any radii. And assuming that the measure is doubling, it's somewhat standard in, for example, harmonic analysis, because it implies that the measure is finite dimensional. So that's kind of like the first things that we need to ask for our space. Now, and this is one of the things that we start to lose when we want to go general. So on metric measure spaces, there is no concept of direction. So that means that partial derivatives have no meaning. So we need to work with something else. But fortunately, we have the concept of upper gradient. So an upper gradient, a non-negative Borel measurable function G, it's called an upper gradient of U if for any rectifiable curve, this inequality holds. Now, if we work for a moment on an Euclidean space in Rn, and we make G equal to the modulus of the gradient, then the modulus of the gradient of U satisfies this inequality. So we can think of upper gradients as a generalization, but they will be a generalization of the modulus of the gradient. So unfortunately, in metric measure spaces, we're gonna lose this linearity that we have with the derivative in Rn. And maybe for existence theory, for existence problem, we don't necessarily feel that loss of the linearity of our derivative, but well, I have had experience with regularity results that we do miss that linearity of the derivative. But okay, so we now have a concept of derivative, right? So we can do, as we do in the Euclidean case, when we define our Sobolev spaces, so function spaces, and the construction is basically the same, so I'm not gonna linger on that, but in this case, we call them Newtonian spaces. So we are on a good track, right? Because remember, we are interested somehow in differential equations where the unknowns are functions. So now we have a house where these functions are gonna live, right? We have function spaces. So we are on a good track. But the last thing that we need for our space is to assume, or we need a connection between the upper gradient, so our derivative, and the underlying measure. And this is why we assume that our space supports a weak Poincare inequality. So we say that our space supports a weak Poincare inequality if there is a constant and a dilation factor such that for any ball, any integrable function, and any upper gradient, this inequality holds. Now, two things about this inequality. Well, notice first that on the right-hand side here, we are indeed working with a dilation of the ball, okay? That's why it's called weak. In case the dilation factor is equal to 1, then it's not weak. And the second one is that, well, this inequality indeed gives us a connection between the underlying measure and the upper gradient, because what this inequality means is that if the upper gradient is small and average, well, then our function cannot oscillate too much. So those are the basic assumptions for our space. So for X to be complete, separable, connected with endowed with a Borel doubling measure mu, and supporting some sort of weak Poincare inequality. So you might be wondering, what examples do you have of such a space, right? So the most obvious one is Rn, endowed with the Euclidean distance and the Lebesgue measure. But if you want to go a little bit different, well, instead of the Lebesgue measure, we can consider a weighted measure. And if you don't want an Euclidean space, then we can think of Heisenberg groups. Also, a popular one is Riemann manifolds or graphs. Okay, so now I do want to talk about one of my projects, so the total variation flow on metric measure spaces. And for this project, I worked with two theories, existence theory, but also regularity theory. But the main goal for this project was to obtain what we call the unifying theory for the total variation flow. And we say unifying because what is usually done, or what was usually done for the TVF, I'm just going to refer to it as the TVF, was that we have some sort of notion of solution, and then we prove existence for that. And then with another notion of solution, we prove regularity, and that's it. Yeah, we're happy with that. But we didn't want that, right? We wanted this overall theory, and not only that, make it even more general by working on this abstract setting. So that is the main goal. And we start with a little bit of introduction and background for this problem, right? Now, in a Euclidean case, the total variation flow corresponds to the following differential equation. It can also be interpreted as the L2 gradient flow of the total variation energy. And also we can think of this problem as the limiting case of the parabolic P Laplacian when P tends to 1. Okay? Now, this problem, the main motivation behind this problem, it's image processing. Okay? And so it's denoising of image. And let me kind of explain a little bit what happens. So remember, so we have our problem, right? So this corresponds to the PDE, and assume that we have some sort of Neumann boundary conditions with some sort of initial image U0, U0. Because we can think of an image as a function, right? We can think, let's assume that this is our initial photo. We can think of this photo as a function from a rectangle to the 0, 1, where each of the points we assign a grayscale, where 0 is white and 1 is black. So we have described a photo as a function, right? So we have our nice looking PDE with non-line boundary conditions with you note our initial photo. And when we solve this equation, what happens, it's a filtering process. And what it does, it denoise the image. Kind of like the outcome will be, well, a denoised image. But what happens is kind of like, it makes it look cartoonish. So what I mean, oh, I'm sorry, I got scared because something moved. So what I mean by that is that if our initial image had sharp edges or yeah, if it had sharp edges, well, you can see that the filtering process doesn't get rid of that. So this process doesn't get rid of discontinuities, okay? It's kind of like what I somehow mentioned with the scalar conservation law, but that means that it is very natural to expect that the existence of solutions or where our solutions are going to live has to be, or it must be related to a space called functions of bounded variation, or BV functions. Now, BV functions are a somewhat more general class than Sobolev spaces. We know that a function, a BV function, it can have discontinuities or even jumps, but they are nonetheless differentiable in a very weak sense. Now, in the Euclidean case, the derivative of a BV function, it's a measure instead of a function. So the first obstacle that we bumped when trying to study this problem was, well, how are we gonna define the space of bounded variation in this abstract setting? Well, there's already some definitions out there, but not only that. Our problem, it's a parabolic problem. So the space where our solution has to live, it's a parabolic function space. So we not only had to have a good looking definition of the BV space, but a nice looking definition of the parabolic BV space on metric measure spaces. But once we have a nice definition of where our notion of solution is going to live, well, we can start, right? So we start with the existence project. So for this one, I work together with Vitor Bufa and Michael Collins, and we have an article. If you're interested, I put the QR code for the archive. So the thing is that, yeah, unfortunately, I didn't explain what the total variation is, but I can say a little bit more with the definition of this solution. So there's something called total variation that also, for instance, in order to define the space of bounded variation, the usual way is, okay, so the functions whose total variation, which is some sort of object there, so it's it depends, but well, there's a definition of total variation for a function. If that is finite, then our function belongs to the BV space. And the thing is that we need that. So our solution, there's going to be involved the concept of total variation in the notion of solution. So so for the existence project, we precisely work with the concept of variational solution. So a variational solution is a function in specific like function class that satisfies this inequality. So what I want you to kind of notice about this definition is precisely, well, this object here is precisely the total variation. Like, unfortunately, I cannot go into much detail about the definition, and furthermore, because we're working on metric spaces, it's a little bit like I would have to go back and define lots of things. But in our definition of variational solution, we have the total variation of our function. And we also have the presence of initial datum, okay? And that's kind of like what I want you to notice right now. So for the existence, we work with variational solutions, and what we proved is precisely theorem 5, which is that there is a unique global variational solution for our problem. And theorem 5 here, it's my favorite one because it precisely uses core variational methods. It's pure direct calculus. What? Calculus of variations. So it's a really nice proof. And we also were able to prove some regularity results for the variational solution. So for instance, we proved that the partial derivative with respect to the time exists, and not only that, that is in L2, also that the function belongs to a certain Holder space. We also have some quantitative bounds as well as some energy bounds, right? So again, kind of like the notion of total variation of the function, it's there. So I mentioned that when working on metric spaces, well, we can expect that it's going to generalize something. So in particular, this existence article generalized work previously done by Verena Bügelein, Frank Tutzard, and Paolo Marcellini in 2015. And again, if someone is interested, I put the QR code there. This is a work done in RN. So that was the existence project. So we can now move on to a little bit like other type of regularity results for the total variation flow. And for this one, again, I worked together with Vito Buffa and my former PhD supervisor, Juha Kinnunen. And again, we have a paper. The archive QR code it's there. And for this project, well, we work with the concept of parabolic minimizer. And well, one thing right away that I want you guys to notice is that, well, the inequality that is involved in this definition is at least shorter than the one for the variational solution. We no longer have a presence of an initial datum, but, well, we still have the presence of the total variation of a function. So we work with parabolic minimizers, and the main goal or the main result was to give a characterization of continuity, necessary and sufficient conditions for a parabolic minimizer to be continuous at a given point. And these conditions are given in terms of, well, sufficiently fast decay of the total variation of our parabolic minimizer near that point, right? So for this, in order to prove this result, we use a De Giorgi scheme. And what do I mean by that? Well, all this Italian school is really good with regularity results and this type of things regarding PDEs. So what I mean about De Giorgi is that, well, we use parabolic De Giorgi classes, the definition of parabolic De Giorgi class. So what happens is that if someone belongs to the De Giorgi class, then as you can see in this case, we say that a function U belongs to the parabolic De Giorgi class if this monster of inequality holds. But this humongous inequality is really important because already the estimates needed, or kind of like the information that we need in order to prove the main result, is encoded there. Like proving that someone belongs here makes it easier on the long run. So when we want to prove the desired regularity results, and that's kind of like what happens. So we work with this De Giorgi scheme using this concept of parabolic De Giorgi class. So the key point in the proof, it's precisely to prove that if someone is a parabolic minimizer, well, then it has to belong to a certain De Giorgi class, because already expect that belonging to the De Giorgi class, it's very nice. It's sufficiently strong, so it will make our lives easier when we try to prove the regularity results, in this case, the necessary and sufficient conditions for continuity. Now, I do want to say one thing. This project was motivated by previous work done by Di Benedetto, Gennat St. Claus in 2017. But the thing here is that Well, when Di Benedetto, Giannazza, and Klaus proved their corresponding proposition 11, they work on time slices. So remember, the total radiation flow is a parabolic problem. That means that our function depends not only on the space, but also has a position with respect to the time, like it depends on the time. So what Di Benedetto, Giannazza, and Klaus did, they froze the time. They kind of fix the time and they work on time slices. They prove their regularity results there, namely that this kind of like frozen in time thing belongs to the Georgi class, and at the end, they integrate it over time. Now, it's a very nice looking argument. It's very, very nice. The thing is that in order to do that, we need a priori to assume some regularity with respect to the time derivative of our parabolic minimizer, which, bear in mind, at the time, we didn't even have existence. We didn't know that this thing existed. We didn't want to do that. So we didn't want to have to assume extra for something that we didn't have at hand. So instead, we went the direct route, and it was a little bit complicated. We used a modification scheme, and this is where we felt the loss of the linearity in our derivative. So very, very briefly, I think, well, I didn't want to write this, but very briefly. So modification, we have just very, we have a sequence of modifiers and modifiers that converge to U, right? But also, I mean, in this case, what we wanted is that the open gradient of the difference, we wanted for this to go to 0. Now, in the linear case, once we have this result, well, the derivative of the difference, since we can open it, indeed it will go to 0, right? Because of linearity. But unfortunately, when working with open gradients, we don't have that at hand. So we needed to do a little bit of other stuff, but at the end we managed. We were able to prove proposition 11 that indeed a parabolic minimizer belongs to the Georgi class. So therefore, we were able to prove the desired characterization of continuity. And with this, we were able to not only generalize symmetric measure spaces, the results by Di Benedetto, Giannazza, and Klaus, but also, well, we didn't have this a priori assumption over the partial derivative. So that was really, really nice. Now, the last thing that I want to comment is, at the beginning, I told you that the motivation for studying the total variation flow on metric measure spaces was to obtain a unifying theory. I gave you this whole speech about, oh yeah, unifying. But so far, what I have told you is, okay, yes, we work on this existence theory with the notion of variational solution, and then also this regularity theory with the notion of parabolic minimizer. Again, what is the unifying factor there? You're doing exactly what everyone does. Well, the nice thing about our existence paper is that at the end, we prove that any variational solution indeed is a parabolic minimizer. So we do have the unifying theory. So that's really nice. And well, what's next? I wanted also to talk about a little bit of the double phase problem. I've been very invested in the double phase problem of metric measure spaces. But unfortunately, because of time restrictions, I won't be able. But I have been working on boundary regularity, a winner type criteria for the double phase problem on metric measure spaces. And also with my Canadian collaborators, we have been thinking about, can we generalize the Monge-Ampere equation to metric measure spaces? Which that's a little bit more complicated, unfortunately, but it's very interesting. And not only that, if someone is interested in doing things, not necessarily on metric measure spaces, but regarding nonlinear PDEs, yeah, we can talk, obviously. So that's it for me. Thank you so much. If you have any questions, I can.
So let's welcome questions, comments.
I think the mic is on.
Okay, the mic is on. So thank you for this talk. I was wondering, you were talking about total variation flow. Do you also have theory regarding no time derivative, just total variation?
So what type of theory? What do you?
For example, take this equation right there and existence and uniqueness if you remove the time derivative.
I think it should hold, right? The thing is, well, I personally don't have that theory, but yeah, I think it should hold. Yeah,
Okay,
yeah.
so what do, okay, so there is also existence and uniqueness.
Yeah. I think adding the time portion is what makes it a little bit difficult. So it should.
Thank you.
Okay, yeah. Thanks for the talk. I was wondering, you mentioned graphs for your setting. Can you say a few words on what the assumptions? Maybe this is a tough question.
Yeah, no, it's
like
fine, it's fine.
What the assumptions look like in graphs. Like, can you have fractals? You would have a finite dimensional only, but how about like fractal structures on the graphs?
Oh.
Do you know?
No, I actually don't know. And actually, it's nice that you mentioned graphs because I forgot to mention that there has been work done for the total radiation flow on graphs. But beyond that, that's kind of like the thing. So specifically for the case of working with graph, I'm not familiar with what type of assumptions we need. But in the morning I was reading this. It's an article by Jose Mazon. So it's precisely like the total radiation flow on metric graphs, and they were talking already about quantum graphs. So I'm not familiar with that, I will say, but there's work done in graphs, definitely. Yeah, welcome.
So when you apply to the image denoising, so is there a parameter to control how smooth or faithful to the original image?
I'm not sure. That's a good question. I am not sure if there's a way to control how much you want.
What there is that how long time?
Yeah, exactly. Maybe with respect to the time. I am not sure, but yeah, I would imagine that it has to be with respect to the time, right? Like I don't want it super like cartoonish, so I will stop here. Yeah, but I am not sure. That's a good.
A quick question about. So I tried to. I just want to confirm with you that you do have uniqueness result.
Yes.
Oh.
Yeah.
So
Uniqueness. Yeah, it was done thanks to a comparison principle.
Oh.
Yes.
It's not less than.
Thank you so much.